Hi, everybody. I'm Colin Pickard.
Oh, I'm Nick P.
I'm Ethan Gutzeit, and that's Cole Anderson with bad Wi-Fi. All right, go ahead, Colin.
So we're group B11,
I am
and we're
Cole
going to do a
Anderson.
talk through of the tank problem submitted last week, Monday. So to get everything started here, to really get a hold on this tank problem, we first have to fill in the blank slots in the inflows and outflows of these tanks. So to do that for this first tank, we have to match the flow out of the tank with the flow into the tank so we can keep a constant capacity within the tank. So to do this, we add the two outflows together. We can have a little equation of the total outflow, which is 11 meters cubed per hour, which has to equal the inflow. And we have a one flow going in of 3, which when we solve that, we get another inflow coming from tank 2 of 9 meters cubed per hour. Then to solve the second one, we're able to find the inflows and outflows of tank 2. Now that we've solved for that 9 meters cubed per hour, we need to solve. One second, guys. Hey, guys, can you oh, crap. Okay, cool. So, sorry, Professor Struthers, for the interruption. So to solve for tank 2, we have to find all of the flows going in and set up an equation for that. We have the tank flowing from tank 3 and the flow from tank 1. Add that together to get, believe it is 11 meters cubed per hour, and have a little algebraic equation to solve the outflow or the inflow, outflow of tank 2 to tank 3 of 2 meters cubed per hour. There we get the get all of our flows going so that our tanks have a constant volume. And I'm gonna hand things off to Nick.
All right, so once we have solved the amount flowing between each tank, we can then set that up as a matrix. And to start that, we're going to first make three individual equations, one for each tank. So for tank 1, we're going to start by calculating the amount of liquid that is flowing into the tank. And we're going to do this by multiplying the flow rate by the mass. So that would, in this tank example, that would be 3 times 12. Now we're going to subtract what's leaving the tank, which is the 4 meters cubed per hour and the 8 meters cubed per hour. And then the final is the mass of the tank. And the mass of the tank is going to be multiplied by the amount coming in. So it's A2 over V2. And then for the second one, we're going to do very similar things. And we're going to get -4 coming in from tank 1. So that's 4 meters per hour times A1 over V1. And then subtract what's leaving, which is 9 meters per hour and 2 meters per hour. And that's coming from tank 2. So that's A2 over V2, which is why that's next to it. And then you have to calculate for what's coming from tank 3, which is 7 meters per hour. Multiply that by A3 over V3 to represent the density from tank 3. Now for tank 3, once again, run through it. The amount entering the tank that is not from another tank is 6 meters cubed per hour. You multiply that by the mass that's given in the problem, which is 8 grams per meter squared. And then you're going to subtract what's leaving, which is, in this case, is 2 meters cubed per hour times A2 over V2, because that's what's coming in. And then you subtract what's leaving, which is, in this problem, 7 meters cubed per hour and 1, which gives you 8. You multiply that by the tank A3 over V3. Okay, so now that we have done all this, that was a lot of words really fast, but we can use this to create a matrix, which will allow us to do many things like calculate the eigenvalues and eigenvectors. And the way we're going to do this is you're going to set everything up that has a variable in it, which is either A1 over V1, A2 over V2, and AV over V3. We're going to set those into each individual columns. And so we're going to get the matrix that you see, A, and yeah, since we haven't accounted for the volume of the tanks yet, you have to remember to divide by all the volumes to get the average flow rate. And then for all the variables that did not have, that didn't carry like specific densities from the tanks, we're going to set that in matrix B, which will also be used later, as you can see down here. And then, yeah, so to find the final A, you're just going to add the volume of each tank into their respective rows and divide it out. And then that's our final matrix of A and matrix B. I'm now going to hand it off to the next guy.
Okay, so now that we've got our matrix A, we're first going to use that to compute the eigenvectors and eigenvalues. Here we've got all the three eigenvectors, W1, W2, and W3. Calculated all of these just using Mathematica, which I've got right here. And then after that, we get the eigenvalues. It's three values, negative 6.49, negative 1.5, and about negative 0.56. And in this case, since yp is a constant, and we use our form of yc to guess what the final answer will look like, we're just going to plug in the eigenvectors and the eigenvalues into our yc and multiply our solve for c by multiplying our vector or our matrix using the eigenvectors multiplied by c, set that equal to y sub 0 minus yp, and that's going to give us our final yp and yc, which will give us our equation. And that's all shown in this matrix here, these big long equations with the eigenvectors in front of the t's and the constant c in front of each of these. And then using this, we have enough information now to plot the behavior and hand it off to Cole.
So then we got a really bad plot right there. Oh, never mind. Now we got a better plot. As you can see, I mean, we got 3 lines for each of the 3 equations, or 1 line for 3 equations. And I mean, they all grow up there, and where they flatten out, the top 2 don't flatten out very much. It's going to take a little bit more time, but where they flatten out, that's like the equilibrium solution right there. And that's where the level of salt is like holding steady in the volume of the tank. The density is sort of or the concentration of salt is staying steady in the tanks. Yeah, it just represents the equation. I mean,
And that's our tank problem.